Okay, I got cut off there on my second half of my talk here. So we're back talking about relational databases here, and we've mentioned entities, we've mentioned fields, we've mentioned records, and of course we came up with a number of different terms for those. Foreign keys, primary keys, composite keys, candidate keys. And just what an entity is, okay, and how an entity uniquely kind of identifies some, it's like a noun, a person, place, or thing, all right, might be a way to think of an entity, all right. So another important concept here is the idea of referential integrity, all right. If we go back and look at, and I'm going to go back a slide here, in order for me to utilize or put an employee in a department, the department needs to exist. I can't have an employee in a department that doesn't exist. Does that make sense? I think it's logic, all right? So what do we do to make sure that doesn't happen? All right, so we have an employee in a department that doesn't exist. That's almost an impossible relationship. And a concept in relational databases we use to deal with that is known as referential integrity. And basically it states that every value of a foreign key must match a value of an existing primary key. All right, so here's their example here from the previous slide. If you have employee 4 in employee, or employee ID equals 4 in employee, and has a department ID equals 7, a foreign key, then there has to be a department out there with a department ID of 7. Okay, otherwise the relationship can't exist. Let's go back and look at this. All right. So if I'm an employee over here and I belong to department ID number 7, that department just needs to exist. I don't think it's too complex, but stop and think about that a little bit. And again, look at the examples, all right? Whoops, let me move you forward here. All right. So here's another perspective. The value of the foreign key, equipment ID in equipment must exist in the value of the primary key, employee ID in employee. All right, so here's another example. All right, and this is what we looked at up earlier here. Okay, so that's the idea of referential integrity. So when you hear referential integrity, it simply means that the foreign key must link to a valid record in the primary key in that relationship. All right, here's another term, and I think I mentioned this earlier on, but let me bring up again a surrogate key. In a lot of cases, we have we don't have a very good primary key. All right, an example I'll use is in the student record system that you guys are really familiar with at the University of Montana. We don't have a way to uniquely identify a student without a surrogate key. All right, so for instance, there's probably 2 Jane Does, Jane Smith, John Doe, John Smith. There's common names. And in order to uniquely identify 2 students, we pick a surrogate key. A surrogate key is simply a primary key that really doesn't have any meaning. It might be a series of numbers. So in the student record system, you have your 790 number. For payroll, we have social security numbers. All right, and those are just kind of, I won't say totally randomly driven, but they're really pretty meaningless numbers unless they're put to a particular entity. Okay, so a surrogate key is a primary key that doesn't really have any particular use, but really is important in relational databases. All right. So here's surrogate key example. If the family member primary key is family ID, first name Sussex, it would be much easier rather than to have multiple multiple fields to uniquely identify that record to create a surrogate key of family member ID. All right, and you can kind of walk through this example here, what the use of a surrogate key could be. Here's another important example, and we're not going to really go through this. I shouldn't say example, a term. But in a relational database, we go through a process as we design it known as normalization. All right, and normalization is where we take a look at our data and we try to understand how it fits together. And we make sure that relations are well formed. So more specifically, if a relation is normalized, rows can be inserted, deleted, or modified without creating update anomalies. Now, let me give you an example here. when we go to address an envelope, we usually put the name, the address, the city, the state, and the zip code. All right? And there's redundant information there because the city and the state could also be represented by the zip code. Or in fact, if you use a 9-digit zip code instead of a 5-digit zip code, that can actually identify the address, the city, and the state. Okay, if we were truly going to normalize a database, we could probably go ahead and create a table with the 9-digit zip code on it that would uniquely identify every single physical location in town. All right, so why would we want that listed twice? Okay, so we could, if we were taking a demographic data of patients, hypothetically, now there's other reasons we don't do this, but hypothetically we could put their name and their 9-digit address down. And we'd have all the information we need on them if we wanted to do a mailing. All right, and that would be a process where we'd normalize that. All right. We don't do that because there's such a human interaction with physical addresses and mail, so we don't put that together that way. All right. So relational design principle for normalized relationship. We want to make sure we have a well-formed relation, and that every determinant must be a candidate key. All right. So in other words, that we're collecting minimum data, and I know I didn't go through determinants with you here, but I'm trying to keep this at a pretty high level here. Okay, so we go through and we normalize, and any relation that is not well formed should be broken into two entities. All right. So if we have a normalization example here where we have a student ID that leads us to the student name, and dorm costs. All right. However, we might normalize that by having a student ID that leads to the dorm name and the student name, but the dorm name might have its own unique dorm cost. Okay, so we would replace that, and you can look at how the structure changes. Okay, where we have now, instead of one entity here, we've created two entities. Okay, where we have an entity here that's ID. That links to the student name and dorm name, and then the dorm name that has the dorm cost. So we actually have a second table here that would allow us to only make one change. If a dorm decided to raise its costs, then we'd only have to change it one place. We wouldn't have to change it in 400 records that have been created for students that live in that dorm. Okay. Again, go through. I'm going through these quickly. Go through the Cronky reading again, and kind of think about those relationships. All right. Lastly, here, this will be the last slide in my presentation here. Here's another normalization example. Okay, so you might have an attorney ID, and you match up an attorney with a client, but we might have more information here that we want to track. So we might have the client's name, the meeting date, and the duration. All right. However, if the client ID leads itself to the client name, which it should, then we can normalize this. So we could go attorney ID and client ID, and then we could just link that to a meeting date and a duration. And we could get the client ID would give us the client name. Okay. So these are the tasks when somebody's designing a database that they go through to optimize it. All right. And it's the normalization process.